Alrighty, hello, we are live. I am live now. For our first office hour of the week. I apologize to everybody who was logged on. We're running a few minutes late. I'm running a few minutes late. I don't know why. I'm referring to myself in the third person plural because there's only one of me. And it looks like there is currently 8 of you. So, good afternoon. Good afternoon, Kate. It's been a long time since we rocked and rolled. I am ready for questions. Hey there. Let's see. When taking the barometric pressure readings, such as millimeters of mercury, is there a certain digit in the ones place? Is that what it says? 3 sig figs. Okay. So, I do not mind at all. So, Kate, the first thing, no, it's no worries. No worries. We should, get into it. So, so the first thing, with, significant figures and, barometric pressure, what determines your number of sig figs is the instrument used to measure. So the instrument determines the sig figs as always. So for example, in when we do in-person labs, and I measure the barometric pressure for the day, the barometer that we have in the lab reads to the first decimal place. So really, so for example, so those readings in millimeters of mercury would have 4 sig figs. Other barometers may only be precise to the ones place. It really depends upon the specific barometer you're using to measure the pressure. For the lab, when they give you like the data, when it's like here's the data to do the lab exercise, you just use the number of sig figs given. But otherwise, you just look at the device that you're reading off of. Sometimes then certain digit is in the ones place, sometimes it's in the tenths place. It can vary instrument to instrument. I don't know if that answers your specific question. Okay. Second question. Excellent. When it comes to hydrogen bonding, the lone pair can be anywhere. So, for example, so it could be on the central atom, like as it is with ammonia. So here, the hydrogen bond, the lone pair for the hydrogen bonding pair of molecules is on the central atom. But for ethanol, for example, there is no central atom. However, hydrogen bonding still totally happens like so. So here's two molecules of ethanol hydrogen bonding, and they totally can, even though the lone pair is not on the central atom. So as long as the molecule has a hydrogen that's attached to oxygen, nitrogen, or fluorine, and a lone pair somewhere in the molecule, hydrogen bonding can occur. Okay, I see there's some Lab 8 questions in the mix. We'll totally get into all of that business. Let's see, practice homework, chapter 7. We've got a couple questions. Oh, you know what? I do not have my textbook in the room. Just give me one sec. I'm going to run and grab it. All right, back in business. So let's see, chapter 7. You know what, I'm going to open my blinds a little bit. There we go. Chapter 7. That's 6. 45. All right, so this is (45A). So let's take a look. All right. All entries in the following table involve pressure, volume, temperature. Data for a sample of gas. Each row in the table is a separate set of data. Use the ideal gas law to fill in the blank. So we're told to use the ideal gas law, which is PV equals nRT, and we're given, the first one, we're not given pressure. So we don't know pressure, but we're given volume. The volume of our sample is 2.00 liters. We're given the moles of our sample, 2.00 moles, and we're given the temperature is 127 degrees Celsius. All right. Now you'll notice here in this problem, we're given volume, we're given moles, we're given temperature, we're asked to find pressure. They do not explicitly give you, whoa, it's the ugliest arrow that I have ever drawn. They don't explicitly give you R, all right, the ideal gas constant, but R is a constant. It's the same every time. It's 0.0821, and its units are liter atmospheres per mole Kelvin. So that is what you will always plug in for R. And you'll notice that the temperature unit here is Kelvin, and the temperature unit given was degrees C. So we need to do a unit conversion and add 273 if all of our units are going to cancel. All right, now 127.273 is, so this adds to actually 400, but The last sig fig for both of these is in the ones place, so we actually have 3 sig figs in this number. So this would be 4.00 times 10 to the squared, 10 to the second Kelvin. All right. And now that we have our temperature and our R, we can solve for pressure, right? We can solve for pressure because we know that PV equals nRT, and we can isolate pressure on one side of this equation by dividing both sides by volume. So we get pressure is equal to our number of moles times the ideal gas constant times our temperature in Kelvin divided by volume. And we have all these values. We have 2.00 moles times 0.0821 liter atmospheres per mole Kelvin. Yes. Yeah, 400 needs to have 3 sig figs because we added 127 and 273. So our last sig fig needs to be right there in the ones place, so we write it in scientific notation. All right, our temperature 4.00 times 10 squared Kelvin. So that last significant digit is right in place. And we divide by our volume, 2.00 liters. And now you'll notice liters cancel liters. Kelvin cancels Kelvin. Moles cancel moles. And we're left with atmospheres, which is a pressure unit. All right, so we have 2 times 0.0821 times 400 divided by 2.00. So the value that I'm getting is 32.84, but we can only keep 3 sig figs, right? We've got consistently 3 sig figs throughout this calculation. So our final answer will be 32.8 atmospheres. And that is the answer for Chapter 7, number 45A. All right. Moving on to Chapter 7. Let's see. 49. Whoa. Let's see. 49. Calculate the volume in liters of. Okay, so right out of the gate, we're told to calculate our volume of 1 mole. Oh, sorry, not 1 mole. 0.1 mole. Okay, let's see. Do you consider the zeros? Ah, right. So, Kate, remember that zeros are sig figs under 2 conditions. First, I should say are sig figs if ... And first, if they are to the right of the decimal and to the right of the decimal and at the end of the number. That's the first condition where zeros are significant. The second condition is if they are between two sig figs. So when you look at 4.00 times 10 to the second, this 0 is to the right of the decimal and at the end of the number, so it's significant. And then this 0 is in between two significant digits. So this number has 3 sig figs. All right, so that is why writing 400 as 4.00 times 10 to the second in scientific notation gives it 3 sig figs. All right, so popping back to number 49. Okay. So we have, we have 0.1 moles of this gas. Our pressure is 2.00 atmospheres. Of course. Absolutely. Anytime. And then we have my least favorite thing. Well, least favorite when they write it like this. 0 degrees Celsius. I just have to say something about this. This makes my head spin because the book spends all this time talking about sig figs, right? And 0 degrees C technically has 0 sig figs. And I want to make you a promise. That is this. I will never put 0 degrees C on any sort of 4-credit assignment. All right. It will always be written as 0.0 degrees C or 0.00 degrees C or some such thing. All right, because when you see 0 in a problem, you're like, that has no sig figs. So then how do we convert it? Add 273, but how many sig figs should the answer have? And it's hard to know, right? So, I totally don't fault you if you found that confusing, because it is confusing and it's sloppy, sloppy of the writers of the book. I believe those are called authors. So I'm just going to rewrite this we have to convert it to Kelvin anyway, right? That's 273 K. Let's use all three of these sig figs and just call it good. So we got 3 there, 3 there, 3 there. Our ideal gas constant has 3. So let's just roll with these and use them to calculate our answer. So, with that diatribe under my belt, let's now solve this problem. All right, now you'll notice that we're being asked for volume and we've been given, whoa, I need to make my pen smaller. We've been asked for volume and we've been given moles, pressure, and temperature. This is beginning to smell like an ideal gas law problem. PV equals nRT. Yeah, totally. Now, R, as we know, is 0.0821 liter atmospheres per mole Kelvin. So we need to isolate volume on one side of this equation. We can do that by dividing both sides by pressure. So we get volume is equal to nRT over P. We have 0.100 moles. We have our value for R, 0.0821 liter atmospheres per mole Kelvin. Our temperature, 273 Kelvin, all divided by our pressure of 2.00 atmospheres. Atmospheres cancel with atmospheres. Kelvin cancels with Kelvin, and moles cancel moles, leaving us exclusively with liters, right? Our volume unit. So now we can crunch our numbers, and we have 0.100 times 0.0821 times 273 divided by 2.00. So we get a nice long value, 1.20665. All the numbers we multiply have 3 sig figs, so we can keep 3. 0 rounds down, so our answer will be 1.12 liters. And that is our volume. All right, so that is the answer for number 49. Let's see, where are we? Okay, 52D, and then we'll jump over to do some Lab 8 stuff. So this is Chapter 7, number 52D. Ooh, loud. Okay, so 52D, determine the following for a 0.500 mole sample of carbon monoxide gas. And part D asks us to find pressure. So that's, what is the pressure in millimeters of mercury for, and then we know it's half a mole, 0.55 moles, 500 moles. We're given our volume. This is in a 2.00 liter container. Our temperature is 25 degrees Celsius, but we got to convert this to Kelvin, so we're just going to add 273 right out of the gate. This will add to 298 Kelvin, and if you look, We added two numbers with their last significant digit in the ones place. Our answer has its last significant digit in the ones place, so we do not need to round. And our ideal gas constant, R, is always the same, 0.0821 liter atmospheres per mole Kelvin. All right, so here we have PV equals nRT. And we need to solve for pressure, right? So we divide both sides by volume, as we're getting kind of accustomed to doing. And we have pressure is equal to nRT over V. We have 500 moles times 0.0821 liter atmospheres per mole Kelvin. Our temperature is 298. And then our volume is 2.00 liters. So let's see. Moles cancels moles. Kelvin cancels Kelvin. Liters. Wait, no, I did green already. Let's do salmon. Liters cancels liters. And we're left with atmospheres. All right, which is good because it's a pressure unit, but we're asked to find our pressure in millimeters of mercury, so we won't be completely done here. But still, it's time to crunch our numbers. We have 0.500 moles times 0.0821 times 298 divided by 2 gives us a pressure of 3 sig figs, 612 atmospheres. I'm just going to double check this real quick. 0.5 times 0.0821 times 298. Yep, divided by 2. Okay, yeah, we're good. Okay, now, so we just have to do one last step, and we need to convert from atmospheres to millimeters of mercury. Now, this is an exact unit conversion, so we don't have to worry about sig figs. 1 atmosphere is 760 millimeters of mercury. So atmospheres will cancel atmospheres. We multiply by 760, and we are in the money. So 6.12 times 760 is 4,651, but we can only keep 3 sig figs, right? So 4,650 millimeters of mercury is our correct answer, the correct sig figs, and the correct units. All right, so that is the answer to Chapter 7, number 52D. All right. Okay, so let's see. We're still way up at the very top. All right, we've got a cluster of questions based on Chapter 8, or not Chapter 8, Lab 8, and then some Chapter 4 questions. But we're gonna, Kate, of course, thank you for asking them. Those were really good practice, really great review, because all that stuff is gonna be on exam 3. All right, so let's take a look. Okay, send an email. Okay, Kate, no, I'm sorry, Susan, let me check my inbox. Okay, office hours, let's see. We're gonna lab 8, attached a picture. I don't think I calculated the molar volume correct. Let's take a look. So, don't think you calculated the molar volume correctly. Okay, let's take a look here. Oof. Oh, you know what I'm going to need? Let's see. Oh, here we go. I'm going to need access to the Lab 8 data sets. There we go. Okay, so let's see. Bum, ba-dum, bum, bum. Sorry, I'm just rearranging my windows. So I have everything we need. Okay, let's take a look. Okay, so this is Lab 8. Molar volume. Okay, so here's the thing. The molar volume of a gas is the volume, it's just the ratio of volume to moles, all right? So it's volume of a gas over moles of that gas. And here, the gas in question is H2, right? It's the volume of H2 divided by the moles of H2. All right? And when it says use the ideal gas law to find the molar volume of a gas, one thing that you'll notice is that, so probably, the easiest way to do this would be looking at the ideal gas law, because you know that PV equals nRT, and if you do a little algebra, divide both sides by volume, you get pressure is equal to nRT over V. But then, if you divide both sides by RT, right, or multiply both sides by 1 over RT, something interesting happens. So we know that volume and volume cancel here, but over here, RT cancels with RT. And you get, oh wait, hang on, I did my algebra wrong. Let me start over. I did the opposite of what I wanted to do. PV equals nRT. I actually wanted to divide both sides by pressure, so I get volume is equal to nRT over P. Then, now I want to divide both sides by number of moles, or multiply by 1 over N. When you do that, you get volume over moles, or your molar volume, is equal to RT over P. All right, so if you take your ideal gas constant, multiply by temperature, divide by pressure, you get your molar volume. All right, this is literally equal to R times the temperature of H2 divided by the pressure of H2. All right, so So we need to use these quantities to calculate our molar volume. So first off, let's look at ambient conditions. All right, so in the question itself, the prompt asks us to calculate the molar volume at ambient conditions. All right. This whole ambient conditions thing, that just simply means like room temperature and pressure. All right, so for example, so just like the normal ambient conditions, molar volume of hydrogen under our normal conditions. So we, in this all right, sorry, just checking to see if I had any new questions. Hopefully you're tracking so far. Let's go ahead and find these quantities. Again, we need the temperature of hydrogen and the pressure. So when we look at our data set, I'm pulling that up right now. We're told our temperature of H2 was 23.0 degrees C. As we know, we got to convert this to Kelvin, so we had 273. So this will be, this will add to 296 Kelvin. Again, we have to round to the ones place. So we have our temperature. Now we need our pressure, which will take a little more work. We're told to find the pressure of H2, we're told the atmospheric pressure whoa. So I need to make my eraser a little smaller. All right, that's good. So you'll notice that we're told what the, I don't want to put that in quotes, what atmospheric pressure is. So atmospheric pressure, we're told, is 765.6 millimeters of mercury. And then you'll notice that we're also told the vapor pressure of water, 21.1 millimeters of mercury. The reason why we're told the vapor pressure is because atmospheric pressure is actually a total pressure. All right. it is equal to the partial pressure of hydrogen plus the vapor pressure of water. So if we want to find the partial pressure of hydrogen, we are going to need to do a little math, right? The total pressure is equal to the partial pressure of H2 plus the vapor pressure of water. We need to subtract vapor pressure of water from both sides of this equation to find the partial pressure of hydrogen. So partial pressure of hydrogen is equal to the total pressure, which is atmospheric pressure, minus the vapor pressure of water. This is 765.6 millimeters of mercury, minus 21.1 millimeters of mercury. All right, so here, 765.6 minus 21.1 gives us partial pressure of hydrogen is equal to 744.5 millimeters of mercury, and we don't need to round because the last sig fig in both of these numbers are in the first decimal place. Our answer has its last sig fig in the first decimal place, so that is totally solid as is. Now, what we do need to do is we do need to convert from millimeters of mercury to atmospheres, because that is the pressure unit in the ideal gas law. So if we want to use this, we got to convert from millimeters of mercury to atmospheres, and 1 atmosphere is 760 millimeters of mercury. So after the unit conversion and keeping all 4 sig figs, our partial pressure of hydrogen gas is 0.9796 atmospheres. All right, so now we have our, you'll notice we have our temperature, we have our pressure. We can now solve for the molar volume. All right, so given that equation that we developed earlier, molar volume, right, which is the volume of H2 over the moles of H2, is equal to ideal gas constant times the temperature of hydrogen divided by the pressure of hydrogen. Ideal gas constant 0.0821 liter atmospheres per mole Kelvin. Temperature 296 Kelvin. And then the partial pressure in atmospheres 0.9796 ATM. And you'll notice atmospheres cancel, Kelvin cancels, and that's it. And that's fine because you've got volume in the numerator, so we should have a volume unit in the numerator, and you have moles in the denominator, so moles should be in the denominator. Those won't cancel, but that's correct for a molar volume. Molar volume has units of liters per moles. All right, so let's crunch these numbers. We have 0.0821 times 296 divided by 0.9796. All right, so there's a big long number coming out. It's 24.80766766. All right, but we can only keep 3 significant figures if you look at the numerator, ideal gas constant, and our temperature. Each only have 3. Our denominator has 4, but you always roll with the fewest. So this would give us for our final answer of molar volume of hydrogen gas is 24.8 liters per mole. All right, and this, again, just for the record, this is the trial one. So I did this calculation with the trial 1 data. I think. Let me check. Yeah. It is definitely a Sorry, I'm not laughing because it's confusing. I'm laughing because you're a cute little cat that's poking out of a box. It is definitely next level challenging. Gas laws are always a little on the hard side. Close, but yet not quite. And so, Susan, I'm looking at your calculations right now because you could be fine. Totally. Okay, Susan, let me see. So you use the ideal gas constant to find your moles. All right. Okay, that was fine. Let me just check something, Susan. Let's see. You know, honestly, question. Okay, wait, hang on, hold the phone 1 second, Susan. I think I may know what you did. Yeah, okay, Susan. I know where you went wrong. So the reason why your number is coming out differently is atmospheric pressure. Was 765. Where was that number? 0.6 millimeters of mercury. If you convert this, it comes out to be 1.007 atmospheres, but this is not the pressure of hydrogen gas. This is the total pressure. So, Susan, the reason why your number is off is you forgot to use Dalton's law, because total pressure, which is, again, atmospheric, is equal to the partial pressure of hydrogen plus the vapor pressure of water. And for this calculation, you need to use this pressure. Really? because I just did the unit conversion. Well then, here's what I would say. Double check it. Yes, that is the one. That's the one. That's totally the one. If you convert that one to atmospheres, because here 744.5 divided by 760 is 0.976. It should be a little bit less. Yeah, totally. So, you are welcome. Thank you for asking a very good, thought-provoking question. Okay, Samantha, you also have a Lab 8 question. Let's see. You're confused on the numbers we use for the pre-lab calculation. That's what ducks do, calculations. Calculations for the pre-lab question 2B. Let's find the molar volume here. Let me just find the pre-lab questions. Pre-lab question 2B. Okay, so in this experiment, partial pressure of water vapor is subtracted from the total pressure. What would happen to the pressure value if this were not done? Explain how the value you calculate for the molar volume of hydrogen would be affected. Okay. Okay, yes. Okay, so Samantha, a couple things. So first off, all the calculations are to be done, the data provided in the Google Sheets doc. Okay, and now then secondly, this one's going to take more explaining than I can type, so we're going to use a picture which is worth 1,000 words. So so this is Lab 8. This is the pre-lab question number 2, part B specifically. But to answer this question, we actually need to do part A. So in this, so we're going to answer part A, and then that answer will illuminate 2B. So if you do not subtract the partial pressure of water, when they say what would happen to the pressure value if this were not done, so if the vapor pressure of water is not subtracted, then logically, if you don't subtract this value, the calculated partial pressure of hydrogen would be too high. All right, that's the answer for 2A. Now, we're going to use this as we move into 2B. So explain how the value you calculate from the molar volume of hydrogen would be affected. Okay, and when they say would be affected, they're talking about would be affected by the partial pressure being too high. Well, we know that PV is equal to nRT, right? And so when we calculate the molar volume, we've done all the algebra, so I'm not going to repeat that here, but we get molar volume is equal to RT T over P, and this is the partial pressure of hydrogen. Now this is where it's going to take a little brain work. If this denominator is too big, right, larger than it should be because we forgot to subtract, then the molar volume, or I should say the calculated molar volume, will be smaller than the real molar volume. All right. If this denominator is too big, this will be too small, or smaller than the actual. Or I'm just going to put too small. If that denominator is too large, that means your calculated molar value will be smaller than the real one. So, and actually, this is an interesting sequence of events. Susan, I bet when you recalculate your molar volume, yep, totally. It is that's just what I was going to say. Susan, your calculations came out too low because you used the wrong pressure to convert. And if you fail to subtract the molar volume, your pressure's too high, which means your molar volume comes out too low. This is a really awesome learning experience where we had a real life example of then the answer to the next question. So how cool is that? And you guys all will get this correct, so you'll get all the points for it. It's a win-win-win all the way around. Yeah, totally. Serendipity can be a fun thing. Okay. All right, let's see. Okay, sorry, Jen. I'm just now seeing your question. And that is yes. Ignore the lab video measurements. Just roll the spreadsheets. All right. Yeah, totally. Okay. Jen, you also asked a question up here, or someone did. Okay, yes, question from chapter 4. Okay, yeah, let's take a look. All right, throwback, chapter 4 question. So let's take a look. All right, so if we have so the comparison is calcium nitride. Now these two ions come together versus calcium carbide. So when carbon has a anionic charge of -4. So I'll just start with the second one. So we need 2 positive 2s to balance our 1 -4, right? You know that we've got to add up to 0 charge. So we need 2 positive 2s to balance with our -4. So that is why we have 2 calciums matched with our 1 carbon. The reason is because 2 times +2 minus 4 equals 0. Right, our total charge has to add up to 0. Now with calcium nitride, let me just make sure I got all of the original question. So with calcium nitride here, whenever one charge does not evenly go into the other, you can simply give the cation subscript will be the anionic charge, the anion subscript will be the cationic charge, and the reason this works is you have 3 times your charge on calcium, which is +2, plus, oops, sorry, I wrote a 3 by nitrogen, it should have been a 2, plus you have 2 times your charge on nitrogen, which is -3. This also works out to be 0 because 3 times 2 is a +6, and 2 times -3 is a -6, and that adds to 0. So in both of these cases, we're looking for a combination of cation and anion that will add total charge to 0. For calcium carbide, +2 goes into -4, so we just need 2 calciums. For calcium nitride, they don't go into each other evenly, and so that's why we do the switcheroo, because that is the only way to get this situation, that +6 and -6. There's whisperings in the videos. That's awesome. Lab quiz. Will there be Lab 8 quiz? Will there be calculations? Will there be free response questions? I don't know. I don't know, but I'm willing to check. Let's see. Yeah, totally. Let me give this a look. Lab quiz 8. Bum, ba-dum, bum, bum. So I've got to look into each problem bank individually. All right, so for lab quiz 8. There is one free response, one conceptual, multiple choice, and 3 calculations. These are also multiple choice. Is that right? Am I missing something? Bum, bum, bum. Yeah. Yep, so that is the tail on Lab Quiz 8. We have a free response, a conceptual multiple choice, and 3 calculations. Well, I don't know what to say to that. Totally. You're gonna do awesome, is what I'll say to that. Project positivity, right? Okay, let's see. Did I? All right, that's so we're actually caught up with questions. Okay, let's see. Will the molar volume of H2 be the same for trap 1 and trap 2 since and vapor pressure are the same for both? Great question. Let me pull. Yep. Totally. So there's not much point in taking an average, is there? Let's see, can I go over how to calculate moles of magnesium and H2? Yes, I totally can. All right, so first off, this is Let's open a new slide. Whoa! So lab 8, I'm going to again be using trial 1 data. So we're given the mass of the magnesium strip that reacted, so 0.023 grams of magnesium. So to find how many moles of magnesium, we just need to use the atomic mass. To go from grams to moles, I think it's 24 or something. Yep, 2431. Grams of magnesium cancel grams of magnesium. And then, so let's see, 0.023 divided by 24.31 gives us 0.00095 after rounding to 2 sig figs moles of magnesium. All right, and then to convert from moles of magnesium to moles of hydrogen, we actually need the balanced chemical equation, which is solid magnesium reacts with aqueous HCl to produce hydrogen gas and magnesium chloride. And so the balanced chemical equation has, we got to multiply HCl by 2, and now it's balanced. Because in the balanced chemical equation, 1 mole of magnesium produces 1 mole of hydrogen, the unit conversion becomes very, very easy. 0.00095 moles of Mg is what we're starting with. We put moles of magnesium in the denominator and moles of hydrogen in the numerator, and the balanced chemical equation tells us it is a 1-to-1 mole ratio. So we end up with 0.00095 moles of H2 for trial 1. And that is how you handle that. All right, so I restate my previous question, which is, are there any new questions? Really? Let me. Oops. Susan, I think where you went wrong is you tried to use the ideal gas law to calculate moles of hydrogen when you've got to calculate it from the magnesium metal source. Yes, you totally do. Let's see. Let's see. Oops. Example problems like problem 7, homework 7. I absolutely can. Let me just pull up homework 7. Wow, you're already cracking on homework 7, eh? Let's take a look. Calculate the grams of sodium hydroxide present. Oh, yeah. Okay, cool. Cool. Yes, this is a great problem. Okay. So I'm going to do, this is like homework 7, number 7. All right, this is like homework 7, number 7. This is fresh baked. Calculates the grams of potassium phosphate present in 10.2 milliliters of 13% mass to volume K3PO4. All right, so we have a solution that's 13% mass to volume. This all hinges on what this means. All right, this literally means that there are 13 grams of K3PO4 in 100 milliliters of solution, and this also means that there are 100 milliliters, for every 100 milliliters of solution, there's 13 grams of K3PO4. You could use it, the ratio, in either way. Now check this out. We know the volume of solution. We know that we have 10.2 milliliters of solution. And when you line them up, what am I doing? I should just cut it off here. When you line these two up, you'll notice that milliliters cancel milliliters, and you're left with grams of potassium phosphate. So we crunch our numbers. 13 times 10.2 divided by 100. It's 1.30. Hang on. .326. We can only keep 2 sig figs, right? Because our percent mass to volume only has 2, so we keep our first 2. 1.3, and our units are grams of potassium phosphate. Different numbers, different compound, but that is the process for solving a problem that is like homework 7, number 7. So that is that business. Yes, totally we can go over molarity. So, molarity is the ratio of the moles of solute to the liters of solution. All right, so molarity just equals moles of solute. Oops. Divided by liters of solution. So that's what molarity is. Ester. Uh, let's see. Okay, so let's take a look. Okay. So let's put this to the test. Again, remembering that molarity is equal to moles over liters. All right, so for example, and I'm just pulling these kind of ideas out of the homework. Determine the molarity of 0.72 grams of sodium chloride dissolved in 3.00 milliliters of water. All right, so here we are trying to find the molarity of our sodium chloride solution, and we know that that's equal to the moles of sodium chloride divided by the volume in liters. So we've got to do two things. You'll notice that we have moles that we want, moles in our numerator, and we're given grams, so we're going to have to do a unit conversion there. The second thing you'll notice is that we want liters in our denominator, and we're given milliliters, so we've got to do a unit conversion there. We've got two unit conversions kind of on our plate. First, let's convert 3.00 mils to liters. All right, we want milliliters in the denominator, liters in the numerator, and the unit conversion here is 1 milliliter is 10 to the negative third liters. All right, so milliliters cancel. And so this is 0.00, after you punch it in, 300 liters. It's important to keep these here because our sig figs shouldn't change. We went from one metric unit to another. Now, to convert our grams to moles, we got 0.72 grams of sodium chloride. We need to know how many grams of sodium chloride are in 1 mole. So we need to calculate our molecular mass. Sodium has an atomic mass of 22.99. Chlorine has an atomic mass of 35.45. So when you add these two together, let's see, that'll be 58.44 grams in 1 mole. So we take 0.72, divide by 58.44, 58.44, and crunch our numbers, comes out to be 0.12 moles of sodium chloride. Because we can only keep 2 sig figs because we started with 2. Now, let's dial this all the way back to molarity. Molarity is equal to moles, 0.012 of solute over volume of solution in liters. So we have 0.012 divided by 0.00300. Now, my calculator is telling me that my answer is just 4, but I know that I need 2 sig figs because of my numerator, so my correct answer with the correct number of sig figs will be 4.0, then my units are molarity. So 4.0 molar, a 4.0 molar solution of sodium chloride would be my final answer there. Let's see. So let's pull another here, let's try doing another problem. Remembering, of course, that molarity is moles of solute over liters of solution. How many grams of HCl are in 15.0 milliliters of a 2.00 molar solution. All right, now you'll notice something here. This problem is a little bit different. We're being asked to find the grams of HCl. Now let's look at what we're given. So we're given a volume, right, 15.0 milliliters. We're also given the molarity. Molarity is 2.00 moles per liter. Specifically, moles of HCl. Now, anytime you're given a quantity that has an algebraic expression, it's worth your while to write that out under your given information because you will probably need this to solve the problem. We know that molarity is equal to moles of HCl over liters. Well, when you look at what we're given, we know the molarity, right? It's 2.00. And we also know the volume, even though right now it's in milliliters, we'll need to convert it. So this equation would allow us to solve for our moles of HCl. And the question is, would we know how to connect moles of HCl to what we're trying to find? Do we know how to convert from grams to moles? The answer is yes, we totally do, right? We can totally convert from grams to moles using a molecular mass. So first step, let's find the moles of HCl. Second step, let's convert those moles to grams. Now you'll notice that to use the molarity equation, our volume has to be in liters, and right now it's in milliliters, so we need to do a unit conversion. 15.0 milliliters needs to get converted to liters. Now 1 milliliter is 10 to the negative third liters. Milliliters cancel. And our volume in liters turns out to be 0.0150 milliliters because, again, we have to keep 3 sig figs because we started with 3. Now that we know our volume, sorry, this is not mils, that's liters. Now that we know our volume in liters, we can take our equation, molarity equals moles over liters, and solve for moles. Let's multiply both sides by our volume. And we find that moles of HCl be equal to the molarity times the volume in liters. Our molarity is 2.00 moles of HCl over liters, and our volume is 0.0150 liters. So here, liters cancel. We can crunch our numbers for moles. 2.00 times 0.0150 gives us a value. Now my calculator is telling me that my answer is 0.03, but I need the same number of sig figs that I started with, right? And I started with 3 sig figs, so this will be 3.0300 moles of HCl. Right, and then to solve this problem, we've got to convert from moles of HCl to grams. And so we're going to need to calculate a molecular mass. Hydrogen has an atomic mass of 1.01. Chlorine is 35.45, so HCl has a molecular mass of 36.46. grams in 1 mole. So now 0.3 times 36.46 gives us a mass of 1.09 grams of HCl. So there are 1.09 grams of HCl in 15 milliliters of a 2 molar solution. All right, so there's a couple examples of how you use molarity, how you solve problems regarding molarity. Let's see, Esther, you've got a question on lab 8. Let's take a look. How did you get the sig figs for the final answer? Let's see. Question. All right, let's see. Okay, let me take a look. Okay. Right. So, okay, Esther, I found the place where your question stems from. Here, give me a sec. Okay, so let's pause that there. Okay, so when you look at the partial pressure of hydrogen, you get this from the total pressure minus the vapor pressure of water, right? Atmospheric pressure minus the vapor pressure for water. And when you look at these two numbers, our total pressure is 765.6 millimeters of mercury minus, let's see, where's that partial pressure? 21.1 millimeters of mercury. All right, when you take this difference, all right, punch it into my calculator, 765.6 minus 21.1. The answer is 744.5. And you have to ask yourself, okay, how many sig figs should my answer have? And when you're doing subtraction, you have to look at the last significant digit in each number. And so both of these have their last significant digit in the first decimal place, the tenths place. And so our answer must have its last significant digit in the tenths place. So that's 744.5 millimeters of mercury, and that's the partial pressure of H2. Now, when it comes to converting the partial pressure of H2 to atmospheres, it's 760 millimeters of mercury is in 1 atmosphere, right? So millimeters of mercury cancel, and this unit conversion is exact. So if we start with 4 sig figs, our answer must also have 4 sig figs, and when you divide 744.5 by 760, the numerical value comes out to be 0.979960526. When you round to 1, 2, 3, 4 sig figs, then the partial pressure of hydrogen gas in atmospheres is 0.9796 atmospheres. So the partial pressure of hydrogen should have 4 sig figs in it. Now, I hear what you're saying. You're saying, oh, I rounded to 3 sig figs and my answer wasn't that far off. Does it matter? And the answer to that question is yes. Because it's exact. Because this unit conversion is exact. It's not measured. So it does not limit your sig figs. It's based off of it's defined, 760 millimeters of mercury is defined as 1 atmosphere. So because that isn't measured, it doesn't limit your sig figs to 2. And then circling back around, the answer to your question, does this matter? The answer is yes, even though our final answer, if I recall correctly, ends up being at 3 sig figs. If you round too harshly too early, it does affect the value. And so in a problem where I ask you to punch in the numerical value, for example, in the exam, which I do from time to time, if your answer is varied because you rounded your sig figs wrong, and you enter that answer into the exam, you'll get the incorrect answer. So you want to follow the rules for sig figs the proper way as you move through a calculation. Just every time. It's just the best way to make sure that you don't lose points when it comes to the test day. Okay. Let's take a look. Let me just pull up the data spread. Yep. All right, homework 6, number 12. Getting stuck on the temperature and moles included in the equation. All right, let me dial this up. So yeah, that's homework 7. Homework 6. All right, consider the mathematical expressions for the gas laws listed. Select the correct name for the law from the response list. All right, let's see. Getting stuck on the temperature and moles included in the equation. Okay, so Susan, here's the deal with so with this one is a problem where I can't like make a problem that's similar to it, but I can give you a prompt that hopefully will nudge you in. Wait. Homework 6, number 12. Hopefully this will nudge you in the right direction. Let's see. Well, so first off, what this question is asking is so written a different way. Which gas law sorry, an even better way to put this is, what is the name of this gas law? And then the equation they give is P1 times V1 times T2 times N2 is equal to P2 times V2 times T1 times N1. And you may look at this aghast. So unfortunately, you cannot ignore unfortunately, you can't ignore the temperatures in moles. That's actually one of the answers. What I would recommend so here's my hint. Is so what this problem did is it took one of the gas laws we learned and algebraically rearranged it. So take a look at the suggested laws and see if you can find the match. I think that's about all the beans I can spill for that one. Without just saying flat out what the answer is. It is one of the answers. So number 9 in homework 7. I can do. This is one of the ones that I can do one that's like it. So here. So this next example is like homework 7, number 9. All right, so a 0.46 molar solution of hydrochloric acid contains 0.300 moles of HCl. What is the solution's volume in milliliters? All right, so first off, identify what you're trying to find. Right, we are after volume in milliliters. Now let's look at what we're given. We're told that we have 0.300 moles of HCl. We're also given the molarity. We're told that we have a 0.46 molar solution of HCl. And remember, anytime you're given a quantity that corresponds to an algebraic equation, write that equation out. Molarity is moles over liters. And if you look at this, we know molarity, we know moles, and we want to find our volume. So we can use the equation for molarity to find our volume. Step one, we need to get our volume out of our denominator. So let's multiply both sides by liters. Second, we now have liters, our volume in liters times molarity equals our number of moles. Let's isolate our liters on one side of the equation. Sorry. Let's isolate our liters, but let's do it by dividing both sides by our molarity. So our volume in liters is equal to our number of moles, which is 0.300, over our molarity, which is 0.46 moles per liter. Moles cancel moles. We can crunch our numbers. So this would be 0.300 divided by 0.46. So this would equal, let's see, 2 sig figs, 0.65 liters. But you'll notice we're not after our volume in liters, we're after our volume in milliliters. So we need to do a unit conversion here at the end. 0.65 liters times, put liters in the denominator, milliliters in the numerator. 1 milliliter is 10 to the negative third liters. So 0.65 divided by 0.65 divided by 10 to the negative third is equal to 650 milliliters. So that would be the volume for this example, which is exactly like homework 7, problem 9. If you execute that problem the way we executed this one, it'll get you there. Yeah! Kate, great question. Great question with a really easy solution, actually. Exactly. Ah. Well, okay. So comparing N2 versus IF is a little apples to oranges because of polarity issues. So let me just look up the electronegativity for iodine really quick. So electronegativities. Nitrogen is 3.0, iodine is 2.5, fluorine is 4.0. So here, the electronegativity difference is 4.0 minus 2.5, which comes out to be 1.5. So IF, because of this, it's polar. So IF has dipole, dipole, and London dispersion. Whereas nitrogen just has London dispersion. So IF wins. So IF has stronger intermolecular forces because because of dipole dipole. All right, but if you were to compare N2 versus I2, all right, N2 just has London dispersion, I2 just has London dispersion, but here I2 has stronger London dispersion because it is larger, i.e. lower on the periodic table. Totally, Kate, you are welcome. The thing to remember here is London dispersion is the weakest dude out there, right? So it's the weakest dude, so you only look at stronger London dispersion forces if two things are tied. But if there's another intermolecular force, hydrogen bonding or dipole-dipole, those will trump. So whoever has hydrogen bonding, strongest intermolecular forces. If there's no hydrogen bonding, whoever has dipole-dipole will have the strongest intermolecular forces. If you have two things that only have London dispersion, that's when you look at which one's stronger. Otherwise, because the strongest London dispersion attraction is weaker than the weakest dipole-dipole. So always look to that last is the take-home message. Okay, Brandon, let me see if I can understand where you're coming from by looking back at the example. Okay. Right, so Brianna, remember, so we've got molarity is equal to moles over liters, all right? And the thing to remember, here is we want to solve for this guy. To solve for a variable, you need to do two things. One, it needs to be in the numerator. And two, it needs to be isolated. All right, isolated on one side of the equation. And the problem here with this equation is we've got both problems actually. We have liters in the denominator and it's with other stuff on one side of the equation. So the first thing we need to do is get our liters out of the denominator, so we multiply both sides of the equation by liters over 1. That accomplishes our first step, which is to get our volume out of the denominator. This gives us liters times molarity on the left side and just moles on the right side. Now, in the second step, we need liters to be isolated on one side of the equation, and that's why we divide both sides by molarity. So molarity cancels here. And this second algebraic step accomplishes the second goal we need to achieve to solve for liters. Namely, we need it isolated on one side of the equation, and we need it to be in the numerator, not out of the denominator, not in the denominator. So that is why we start by quote unquote canceling liters. We're just moving it to the other side of the equation. We're jailbreaking it out of that denominator that it needs to escape so badly. So this would be step 1, step 2. So that is the reason why. Awesome. Oh, you are very welcome. Anytime. I totally can. I think. Let me pull it up. Let's see. So a gaseous mixture at a total pressure of 1.5 atmospheres contains equal molar amounts of helium, neon, and argon. At constant temperature, CO2 gases added to the mixture, until the total pressure is 3 atmospheres. trying to think if I can cook up an example that's like it but different. Okay. So I don't know that I can cook up an analogous problem, but let me give you some food for thought. So this is homework 6, number 8. So we have a sample of gas containing helium plus neon plus argon. Pressure 1.50 atmospheres. Now we're going to add CO2 constant temperature. Sorry. So our temperature has not increased. So now we have helium plus neon plus argon. And there's a critical piece of information. They tell us that we have equal helium, neon, and argon. All right, that means moles of helium equal moles of argon equal moles of neon. All right, so now we have plus CO2, and our pressure now is 3.00 atmospheres. This is P1. This is P2. So here are the things to note. First, our pressure has doubled. What does that tell you about how total moles of gas has changed? All right. If you need another prompt, look back in lecture to see how pressure and moles are related to each other. All right, and that's about all I can say with that. All right, Esther, your question about the final answer for the molar volume. So remember, molar volume is volume over moles, right? It's the volume of a gas divided by the moles of a gas. And I'm not going to repeat the algebra here because I did it earlier in the office hours, but from the ideal gas law, you can rearrange the ideal gas law so that it says molar volume is equal to R times T over P. When you solve the ideal gas law for molar volume, that's what you get. And R, our value for R has 3 sig figs. Our value for T also has 3 sig figs. And then our partial pressure of hydrogen has 4 sig figs. So when you take these 3 into account, your answer would have 3 sig figs because you got to roll with the least. Ah, Esther, great point. If you use the value for R that you calculated, then it totally should have 2 sig figs in the end. Totally. Susan, thanks for dropping by. Catch you tomorrow. Yep. Oh, Esther, great question. I thought I already did, but maybe I forgot to upload them. Let me take a look. Oh, you know what? Thank you for the reminder. I totally have them done. I just forgot to post them. There we go. Yep. Hang on 1 second. There we go. Alrighty. Just uploaded them to Canvas. Alrighty, well, I'm gonna go ahead and call office hours here. Thanks everybody for showing up, asking awesome questions. I'll catch you all tomorrow in lecture. Later.